Hello, welcome back to the problem solving session of NPTEL Thermodynamics course. I am Pradeev, I am one of the TA for this course. Today we will solve some problems on the week 5 portions, which is mainly on gas mixtures. So first I have a problem. The first problem we will solve is given here. The rigid tank contains 8 kilomole of oxygen and 10 kilomole of carbon dioxide gases at 290 Kelvin and 150 kilopascal. Estimate the volume of the tank. So this can be solved directly using ideal gas equation. We know the ideal gas equation is given by PV equal to mRT. Since in the problem it is given in moles, I will write the molar formula. So PV is equal to nRT, where n is the number of moles and R is universal gas constant and temperature, pressure and volume. So to calculate the volume occupied by oxygen, I can write pressure PV. Pressure is 150 kilopascal for both the gases, and volume of oxygen is equal to number of moles of oxygen, which is 8 kilomole, and universal gas constant is 8314, and the temperature is 290 Kelvin. So with this I can calculate the volume occupied by the oxygen in that rigid tank. So this gives out this comes to be 128.59 in meter cube. Similarly, I can calculate the volume occupied by carbon dioxide, which will be I can write this as number of moles of CO2 into universal gas constant by into temperature by pressure, which is 10 kilomole into 8314 into 290 divided by pressure, which is 150 kilopascal. Writing into pascal, I have put 10 power 3. So this is calculated as this is 160.73 meter cube. So this way I can calculate the total volume of the tank. So volume of the tank is volume occupied by oxygen plus volume occupied by CO2, which is 128.59 plus 160.73. So this is 289.32 meter cube. Was that clear? Or if you have any doubt, please ask me.
Sir,
yes.
Do we need to calculate R particularly for each gas and then proceed, or
Sorry, calculate R of
each gas for oxygen?
So here, since it is given in number of moles, the R we are interested in is the universal gas constant.
Okay.
Which is joule per kilomole Kelvin. So in this R is joule per kg Kelvin. So since it is given in moles, I can use this universal gas constant, and I can calculate directly. So I need not calculate the characteristic gas constant R.
Okay, sir. Okay. Nice.
So here, since the pressure and temperature are same, I can also say that total number of moles is can you mute yourself? Sorry.
Huh.
So I can also say the total number of moles in the tank is given by number of moles of oxygen plus number of moles of carbon dioxide, which is 8 plus 10 is 18 kilomoles. So since both are at the same pressure and temperature, I can also write the equation for this. P V is equal to N total R bar T, and then if I calculate V, then this will be the same. So it will be 18 into 8314 into 290. I hope there are no other questions. Then we move to the next problem. So in this problem, we have a rigid tank which contains 0.5 kilomole of argon and 2 kilomole of nitrogen at 250 kilopascal and 280 Kelvin. The mixture is now heated to 400 Kelvin. Determine the volume of the tank and the final pressure of the mixture. So to solve this, I would again start with the ideal gas equation. PV is equal to N R bar T. So here I know pressure is 250 into 10 power 3 pascals. Temperature is 400 Kelvin. I know N is 0.5 plus 2, which is 2.5 kilomole in total. Sorry, temperature is initially 280 and finally it becomes 400. So with this, if I want to calculate the volume, I would have N into R bar T divided by pressure. So this is 2.5 into R bar is 8314 into temperature 280 Kelvin divided by pressure of 250 kilopascal. So this way I can calculate the volume. Which is 23.28 meter cube. Now it is said that the final it is heated to a final temperature of 400 Kelvin, and then I need to calculate the final pressure of the mixture. So this again, applying this PV equal to nRT, I have P into the, since it is a rigid tank, the volume doesn't change when we heat. So I can take the same volume as the initial volume is equal to N, number of moles wouldn't have changed, into 8314 into 400. So pressure would be 357 into 10 power 3 Pascal. This is 357 kilopascal. Any questions?
No, sir.
In the next problem, we have a gas mixture at 350 Kelvin and 300 kilopascal with the volumetric analysis of 65% nitrogen, 20% oxygen, and 15% of carbon dioxide. We need to determine the mass fraction and the partial pressure of each gas. So to calculate the partial pressure, I can write, say, partial pressure of component I or gas I is written as mole fraction of I into total pressure. So this I can get it directly. So first I will start with calculating the partial pressure of each component. So partial pressure of, say, first is nitrogen, is equal to X of nitrogen, or the molar fraction of nitrogen, into total pressure. So this is it said volumetric analysis. So the 65% of nitrogen means 65% of nitrogen in terms of volume. So in total volume there is 65% of nitrogen gases. So as per Avogadro's law, we can say the equal moles of gases consume or consumes equal volume. So with that, we can say volumetric percentage is same as molar ratio. So this is 0.65 into P total is 300 kilopascal, or I would have it for this problem everything in kilopascal. So this would be 195 kilopascal. Similarly, partial pressure of oxygen is equal to molar fraction of oxygen, which is given as 20%. So it is 0.2 into total pressure of 300 kilopascal. So this is 60 kilopascal. And partial pressure of carbon dioxide is 0.15 into 300, which is 45 kilopascal. Now we need to determine the mass fraction. So mass fraction Yi is given as molecular weight of I by molecular weight of mixture into Xi. So Xi will be in mole per mole, and molecular weight will be in gram per mole. So this will be again in gram per mole. So when we multiply gram per mole into molar fraction, we get the fraction of the mass fraction of the mixture of the gas. Now for this calculation we need the molecular weight of the mixture. So to calculate the molecular weight of the mixture, we need to calculate molecular weight of the mixture can be calculated by multiplying the molecular weight of the individual components with the molar fraction of individual components, and summing it up, we will get the molecular weight of the mixture. So this is in gram per mole and this is in mole per mole. So multiplying or this I would say this is mole of I divided by mole total or mixture. So now if we multiply this gram per mole with the mole mixture, we will get finally gram of the mixture by mole of the mixture. So I will start writing this. for the first component I have nitrogen. The nitrogen's molar fraction is 0.65 into molecular weight is 28 plus 20% of oxygen, so it is 0.2 into 28 plus 15% of carbon dioxide, which is 0.15 into 44. So for I'll just say how to find the molecular weight. Molecular weight for nitrogen, we know that the atomic number is 14 for nitrogen, so or the atomic mass is 14, so nitrogen, which is 2 of nitrogen, so it will become 2 into 14, which is 28. So molecular mass of nitrogen is 28, and same goes with oxygen. Each oxygen weighs 16 grams, so 16 gram per mole. So oxygen molecule O2 will be 2 into 16, which is 32. And for carbon dioxide, it is, for carbon it is 12 plus 2 into oxygen, which is 32, 16, which is 12 plus 32 becomes 44. So for carbon dioxide it is 44 gram per mole. So summing this up, I have 31.2 gram per mole of the mixture. So now I need to calculate the molar fraction, mass fraction. So mass fraction is given by y. Yn2 is x n2 into molecular weight of n2 divided by molecular weight of mixture, which is 0.65 into molecular weight of nitrogen is 28, molecular weight of mixture is 31.2 if I'm not wrong. So this is 583 or 58.3%. Now mass fraction of oxygen is molar fraction of oxygen into molecular weight of oxygen divided by molecular weight of mixture. Hello.
The molecular weight of mixture.
Can you see my screen now?
No. The molecular weight of mixture.
Yes.
I'm getting as 30.4.
Sorry?
In the previous slide, molecular weight of mixture.
Yeah. So this is molecular weight of mixture is given by summation of
31 point. I'm getting is 30.4.
30.4. Okay, let me check.
Yes, sir.
Sorry. This should be oxygen's molecular weight. Now is it right?
Yes, sir. Yes.
Yeah. Thank you. So if I'm going fast, you can let me know. I can slow down.
No, sir. Yes, okay.
Now molar fraction of oxygen is 20%, so 0.2 into molecular weight of oxygen is 32 divided by 31.2. This is 0.205 or 20.5%. Now I can calculate molecular weight of carbon dioxide, which is molar weight of carbon dioxide into molecular weight of carbon dioxide divided by molecular weight of the mixture. So this is 0.15 into 44 by 31.2. So mass fraction of carbon dioxide is 21.1%. If there is any mismatch in your calculation, please let me know. We can figure it out.
No, sir. No, it's okay.
Now, next problem, we have a certain gas with the CP of 1.968. Not sure if this is, yeah. CP of 1.968 and CV of 1.507 kilojoule per kg Kelvin. We need to find the molecular weight and the gas constant. So we know the relations between CP and CV. CP minus CV is R, and R is obtained by universal gas constant by molecular weight. So this is very simple. Now R is CP minus CV in kilojoule per kg Kelvin. So this is 1.968 minus 1.507. Since this is in kg, I multiply it with kilojoule. I am multiplying it with 10 power 3. So this will be 461 joule per kg Kelvin. Now I can calculate the molecular weight by using this formula. 461 is equal to 8314 divided by molecular weight. So that means molecular weight is 8314 divided by 461. So this is 18.03 gram per mole. Can anyone of you guess which molecule's molecular weight is 18 gram per mole? Okay, so molecular weight of H2O is 2 into 1 plus 16, so this gives 18 gram per mole. So this is very close to H2O, so probably the data is for the water. If you don't have any questions, I can move on.
No, sir.
Okay. Now yeah, we have a problem. Two vessels A and B, both containing nitrogen, are connected by a valve which is open to allow the contents to mix and achieve an equilibrium temperature of 27 degrees Celsius. So if I have to draw the schematic, so two vessels A and B are given. So before mixing, the following information is known about the vessels in the two gases in the two vessels. So both have nitrogen The pressure is given as 1.5 megapascal for content vessel A, and it is 0.6 megapascal for container B, and the temperature is 50 degrees Celsius. So 50 degree plus 273 is 323, so I take it as 323 Kelvin, and here it is 20, so it is 293 Kelvin, and this contains 0.5 kg mole of nitrogen, and this vessel B has 2.5 kg of nitrogen. Calculate the final equilibrium pressure and the amount of heat transfer to the surroundings. If the vessel has been perfectly insulated, calculate the final temperature and pressure which should have been reached. Take gamma as 1.4. So in problems like this, when there is a mixing of two gases, we can assume that the initial internal energy given by U is equal to final internal energy. So I can write this as Ui is equal to Uf. This internal energy, initial internal energy, means the internal energy of the whole system. So this will have internal energy of A, UA plus UB, and if it is final, I can call it as AB, which is combined after the mixing is done. I can call it as UAB. So this U is again given by CV into T. So CV MCVT, this is for A, plus MB CV TB. Here both the vessels have the same gas of nitrogen, so I need not say distinguish it as CVA and CVB. I have taken it as common, and so finally final internal energy is given by MAB, which is the total mass into CV into TAB. So this is considering there is no heat transfer out of the system, but here they have given there is some amount of heat which is transferred, and the final temperature has become 27 degrees Celsius. So we need to calculate the final heat, we need to calculate the heat that is transferred to the surrounding. First, finding the final equilibrium pressure is simple, which can be done by PV equal to MRT equation. Here we need to know the here the pressure, final pressure is what we need to calculate. The volume we can calculate individually and we can add it up. Mass also we need to calculate individually and add it up. So for the mass of the vessel B is already given. Mass of vessel A is to be calculated from the 0.5 kg mole. And so R is known, characteristic gas constant. We can calculate by having universal gas constant divided by the molecular weight. And temperature, final temperature is given. So I need to calculate the initial volume of the vessels VA and VB. So for the initial condition PA, VA is equal to MARTA. So to calculate this MA, I know it is 0.5 kg mole, divided by the molecular weight will give me, multiplied by the molecular weight will give me kgs. So this is 0.5 kilogram mole into, for nitrogen the molecular weight is 28 gram per mole. So this will be 14 mole get cancelled, and we will be left with so this should be written as, since it has a kilogram mole, we should write it as 0.5 into 10 power 3 uh, gram per mole. So this will be 14 into 10 power 3 kg. No, grams. So it is 14 kg. So 1 gram per mole, sorry, 1 mole of nitrogen will have 28 grams. So this is generally 1 gram mole, which is 28 gram. Now 1 kg mole of nitrogen will have 28 kilograms, sort of 0.5 kg mole, yeah, so 14 kg. So this, we have found the mass of nitrogen which is present in the vessel A. Now we can calculate the volume of vessel A. So VA is given by MA or TA divided by pressure of A. So VA is, mass of vessel A is 14 kg into characteristic gas constant is given by universal gas constant divided by the molecular weight. So molecular weight of nitrogen is 28 into initial temperature is 323 Kelvin, and initial pressure is 1.5 megapascal. So writing in terms of pascal, I will have 1.5 into 10 power 6. So VA is 0.895 meter. Similarly, I can calculate VB, which is MB R into TB divided by PB. So mass of this second vessel is 2.5 kg. 2.5 kg into 8314 by 28 into temperature. Temperature is 293 Kelvin and pressure is 0.6 megapascal. So I will have VB as so VB is 0.362 meter cube. So we have calculated VAB, that is a total volume of both the vessels. Now we need to calculate the final equilibrium pressure. So the final temperature is given as 27 degrees Celsius. For this we need to calculate the final equilibrium pressure. So we can use PV equal to MRT equation. So now it is PAB, AB and MAB, TAB. So pressure AB is equal to MRT. So mass, total mass is 14 plus 2.5 into R is 8314 by 28 into TAB is 27, which is 27 plus 273 Kelvin, which is 300 Kelvin, divided by final volume. The final volume is a total volume VA plus VB, which is 1.257 in the denominator. So this is 1.169 into 10 power 6 pascals, which is 1.17 megapascal. Now we need to calculate the final temperature, assuming the vessel is perfectly insulated, and in that case we need to calculate both the final pressure and the temperature. So for this we can make use of this equation. Initial internal energy of the system should be same as the final internal energy of the system, because there is no heat transfer. But I think before that we need to calculate the amount of heat that is transferred to the surrounding in this case. So for that we can calculate the initial internal energy. So we need the CV to calculate the internal energy. CV is given by R by gamma minus 1. For nitrogen, gamma we can take 1.4 as gamma. So this is 8314 by 28 divided by gamma minus 1 is 0.4. This is 742.3 joule per kg Kelvin. Now the initial internal energy is UA plus UB, which is MA CVTA plus MB CVT2. MA is 14 kg. CV we can take it common outside, and we know TA is 323 Kelvin plus MB is 2.5 into TB is 293 Kelvin into CV, which is 742.3. So we know the initial internal energy. .91 megajoules. To calculate the final internal energy, UF is UAB, which is mass of AB CV into TAB. Mass of AB is 14 plus 2.5 into CV is 742.3 into TAB is 27 degrees Celsius, which is 300 Kelvin. So final we have 3.674 megajoules. So So heat that is transferred is final internal energy minus initial internal energy, which is 3.674 minus 3.91 megajoules into 10 power 6 joules, which is point 236 into 10 power 3 joules, 10 power 6 joules. To 36 kilojoules. So the final internal energy is lesser than the initial internal energy, so that means the heat is transferred out of the system to the surrounding air. So we write it as negative. Q transferred by the system is negative. So next is to assume no heat transfer and then calculate the pressure and temperature, final pressure and temperature. If there is no heat transfer, we know Ui is equal to Uf. Ui we know it already, 3.91 into 10 power 6 joules. V final we can calculate using MCVT. MAB, so this is MAB into CV into T final. So MAB is 16.5, which is 14 plus 2.5, into CV is 742.3 into TF. So TF can be calculated. Which is 319.24 Kelvin. So when there is no heat transfer, we had with heat transfer to the surroundings we had 300 Kelvin. Without any heat transfer, we have a final temperature of 319 Kelvin. Now using the PV equal to MRT equation, we can calculate the final pressure. P final is MRT 16.5 into 8314 by 28 into 319.24 divided by the volume. We have the total volume. Yes, we had a total volume here 1.257 meter cube. This comes to be 34.84 into 10 power 6 Pascal, which is 34.84 megapascal. This doesn't seem to be right. Okay, anyway, if I find out the problem, I would come back in the next session and solve this. There is only 10 minutes left and the live session is interrupted due to network issue. So I would stop here and we will meet in the next session. Thank you.